Okay, so this is the second half, or really it's questions 11 through 23 of the test review for the final. This is basically all of the trigonometry that we did in Algebra 2 that we're going to test on this semester. And number 11 starts with a right triangle that looks a little like this. There's a 5 here, a 12 here, and I put theta up there. And your job is to write all 6 trig ratios for theta. That's the sine, cosine, tangent, cosecant, secant, cotangent. In order to do that, I have to find all 3 sides. So I'm going to start with Pythagorean's theorem. Because I know the 2 sides and I don't know the hypotenuse, it's just a squared plus b squared equals c squared, c being the hypotenuse. So I can do 5 squared plus 12 squared equals c squared. That's 25 plus 144 equals c squared. That's 169 equals c squared. Now, here's where we take a square root, and there's a little bit of a catch. If 169 does not have an exact root, we try to break it down a little bit at a time, looking for perfect squares like 4 or 25, things like that in there. Right now, 169 does happen to have a square root that's 13, which means I'm just going to put the number 13 there. There are times where it might be something like the root of 11 or something along those lines that goes there. So if you have other questions about reducing roots, we could talk about that maybe a little bit later. But when we start to do the sine is defined as the opposite over the hypotenuse. Well, the opposite side from theta is 12 over the hypotenuse is 13. And then the cosine of theta is defined as the adjacent side, which would be 5 over the hypotenuse of 13. Tangent is, of course, opposite over adjacent. That would be 12 over 5. And then we have the reciprocals. Cosecant is 13 over 12. Secant is 13 over 5. And cotangent is 5 over 12. That is what question 11 is asking you to produce. Now 12 is a little bit of a follow-up, so I'm going to stay here. Question number 12 says, what is theta? It says, for what value of theta is the triangle above possible? I'm just asking for what theta equals in that triangle. Well, if we know that the sine, I'm just going to pick the sine. I could pick cosine or tangent, but let's say the sine of theta equals 12 over 13. The question is, how do we isolate just theta? Well, to do that, we're going to have to remove this sine function. To remove a sine function, we use a sine inverse. And so I'll take the sine inverse of both sides, and that should give me theta all alone. So I'm going to grab my calculator, and I've already checked that my mode is in degree mode. It's important you're aware of that. I'm going to take second sine of 12 over 13. And I get 67.38. Now, if I had chosen the cosine, which was 5 over 13, and I did second cosine of 5 over 13, I get the exact same answer. And same thing with tangent and tan inverse. So it's a 67.4 degrees would be my answer for 12. So that's your basic right triangle trig that we would have pulled from basically what you did in geometry. Now, 13 and 14 are a little bit more involved. They required the law of sines and law of cosines. And your job is to find A, B, C, little a, little b, and little c. To start out, your given angle B is 35 degrees. And you're given that little b is 12. We know that it's little b because in the picture it's directly across from the angle. And then little c is given as 8. Which means I'm going to have to find big C first because I have all of this information and I'm only missing the C. The law of sine says that the sine of an angle, let's say B, 35, divided by its opposite side, 12, will equal the sine of another angle from that same triangle, we'll call it C, divided by that angle's opposite side, 8. To solve for C, I first need to get rid of this 8, so I'm going to times by 8. And I'll go to my calculator. Notice I'm writing down that this is not solved. I still have the sine of C equals. Grab my calculator, and I'm going to do 8 times the sine of 35 divided by 12. Notice I close those parentheses. So I can do this. I get 0.382. Well, I don't have c alone yet because I still have to take the sine inverse. If I take the sine inverse of that, I'm going to go second sine, second answer, and I get 22.48. I'm going to go ahead and, I'll stick with 22.48. That's fine. So let me erase this question mark, and we'll put 22.48 right there. So now that I have all that information, I should be able to figure out big A, because I know that there's 180 degrees in a triangle. So if I take 35 plus 22.48, and I do 180 minus that, I'll get 122.52. So that's 122.52 degrees. Make sure those add up to 180. I'd hate for you to get something wrong just because you didn't do that. And then I'm going to use the law of sines again. But because I'm looking for little a this time, so now I'm going to work on, say, this information here. Because I'm looking for a little a, I'm going to put little a on top and put the sine of big A on bottom. You're always allowed to flip it as long as you flip everything. So over here, I'm not going to put sine of b over 12. I'm going to put 12 over the sine of 35. So you can see how that fraction got flipped upside down. Again, I'm going to multiply by the sine of 122.52, because that's what I would do to cancel this on the left-hand side. Well, a then ends up completely alone. So if I can calculate this, it's 12 divided by the sine of 35 times the sine of 122.52. I'm going to get 17.64. And I am done. There's all the information about the triangle, A, B, and C. Now, on question number 14, it's a little bit more involved. I can't use the law of sines right away. If you look at the triangle, you don't know A, you don't know B. C is given as 60 degrees. Little a is 8. Little b is 4. And little c is unknown. Because I don't have both A's, both B's, or both C's, I needed both of something to use the law of sines. And since I don't, I'm stuck using the law of cosines. When you use the law of cosines, it always starts with the little letter that you're looking for, or the angle that you're looking, the little letter that matches the angle that you're looking for. Because I know about big C, I'm going to start with little c. And it's c squared equals a squared plus b squared minus 2ab cosine of capital C. You could change the a's to c's and c's to a's, or the a's to b's and b's to a's. You could change any one of these to the other to get the other versions. I would just write the formula down on my circle, have it as a resource. But in this problem, c squared will equal 8 squared plus 4 squared minus 2 times 8 times 4 cosine of 60. Now notice everything over here is a number. There's no variables left. So I should be able to throw that all into the calculator. Get c squared equals, let's find out. It starts with 64 plus 16 minus 2 times 8 times 4 cosine of 60. I close that parenthesis, hit enter, I get 48. Remember though, that's not my answer, so I'm going to take the square root here. Now, a lot of times we don't use decimals when we're using square roots, but where this is a measurement of a triangle's side, I think we're going to go ahead and use a decimal here, 6.93. So little c is 6.93. And now if you look, hey, we have both c's, we can go after a or b. Now the law of sines will not produce an obtuse angle. So if I'm choosing between a and b, I'm going to pick b because it has the smallest side. That means I'm going to get an acute angle that's less than 60, which I like. There's a possibility that a might be obtuse, and I wouldn't know that unless I do it this other way first. This is the quickest way. I'm going to take the sine of big B over 4 equals the sine of big C, which is 60, over little c, which is 6.93. Like last time, I'll times by this bottom value, and I'll get the sine of big B equals, and there will be a number that comes out of my calculator for this. Take the sine of 60 divided by 6.93 times 4. And I get 0.49987. 0.49987. And again, we're going to have to apply that sine inverse. Sine inverse. And if I do that, second sine, second answer, I get 29.99. Honestly, I feel like I'm going to have to round that to 30. Maybe I'm off a little bit. Let's go ahead and call that 30 degrees. Now by subtraction, it turns out this is a 90-degree angle. The fact that it was a right triangle meant that we actually could have used right triangle trig to solve it, but that is no guarantee that that's going to happen. In fact, I would almost bet against that happening, okay? So just be prepared to use law of sines and law of cosines. Don't make assumptions about right triangles. All right, so we turn the page, and we're going to graph 3 graphs, okay? 15, 16, and 17 are all graphs of different sine, cosine, and tangent waves. So as we start, question number 15, we have y equals negative cosine of 2x. Two things we typically look for are the amplitude, which is always the number in front of the trig function. In this case, it's a -1, but we always take the opposite value, so it turns out to be a 1. And then the period for a sine or cosine is 2 pi over b. B is the number that's multiplied by x. That'd be 2 pi over 2, which is just pi. Okay, so when I go to do the graph, okay, I'm going to go out 4 marks, label the period, that's pi. Halfway is half of that, and then half again to get to the quarter. And then there's 3 of those marks, so we call it 3 pi over 4. And then I've got 1, 2, 3, 4 marks to the left. Again, that's negative pi. And I could label all those if I needed to. Up here is 1, down here is -1. Now, cosine wave traditionally starts at its amplitude. But because this is negative, I'm going to start at the negative version of the amplitude. And then I'm going to go to 0, then up to the positive amplitude, back to 0, and back to where I began. And I can mimic that over here on the left as well, creating this smooth curve. You need to know where the trig function starts and its basic behavior through these 5 points. I do expect you to do both the left and the right-hand side. 16 is the sine wave. It's very similar with one small difference. Sine of pi x. The amplitude here is 3, and the period is 2 pi over b, but b in this problem is pi. The pi's cancel, and we get 2. Meaning, if we go out 1, 2, 3, 4 marks, we should be at 2. So 1 at the halfway, 1/2 for half of that, and 3 halves between 1 and 2. 1, 2, 3, 4, -2. Up to 3, down to -3. Now a sine wave does not start at the amplitude. It always starts at 0 or the midline. Now because it's positive, it's going to go up first. If it was negative, it would go down first, and then back to -3 and back up. And if I mimic that backwards, it's going to kind of follow this same pattern to the left so that you can see the wave nature of the sine wave. I mean, there's not a lot else to it. If you follow the same steps every time, you'll get through it just fine. Now 17 says y equals 2 tangent of x over 2. I'm going to rewrite that as 2 tangent of 1/2 x. When you talk about finding b, it's always important you realize it's what's multiplied by x. Well, x is being divided by 2, which is the same as multiplying by 1/2. There is no amplitude for a tangent wave. It's infinitely tall, but its period is always pi over b, which in this case is pi over 1 over 2, which we flip in times to make 2 pi. So my period on this tangent curve is going to be 2 pi. So 1, 2, 3, 4. Call that 2 pi. This would be pi. This would be half of pi. And this would be 3 pi over 2. And I can do the same 4 marks to the left. Negative 2 pi. Now, as a side note, the tangent, it's the weird one. It has asymptotes at the second mark on both sides. And then it would have that asymptote again in 4 more marks. So you'd think 1, 2, 3, 4. There'd be another asymptote. And over here on the left, 1, 2, 3, 4, another asymptote. The reason I like drawing that is just because it has, I can see the cycle repeat itself if I do it that way. Tangents typically cross in the center. And because this is a positive 2, it's going to go upward as it goes to the right. So I'm doing something like that, except it's supposed to cross through there. It would cross through again at 2 pi and at negative 2 pi. Some of you only like to graph the first parts, and so technically if you had this piece here on what I drew on the right just now, that's technically enough if you had it also on the left right here down to the point. But I like the repetition, so I like to draw it up like that so I can see the sequencing and the repetition there. Number 18 and 19, they're the trig identity problems, and really this is about, do you have all the trig identities either memorized or written down, and have you done enough of them to get practiced at it? So if we look at number 18, oops, now I'm losing my marker. Okay, it says we have the tangent. Oh, hold on just a second. Okay, so back at it. Okay, number 18, it says that we have the tangent of x, the sine of x, and secant all multiplied. So sine, secant. They're all being multiplied, and so because this isn't Pythagorean in nature, which would have a square on it and some sort of pluses or minuses, I'm really looking at making things into sines and cosines, or at least similar functions, and seeing if things cancel. Okay, so a tangent is sine over cosine, by definition. A sine I like, so I'm going to just put sine over 1, just so it looks like a fraction like the rest. And secant is defined as 1 over cosine. Now, if I look, I don't see stuff that's going to cancel, because a sine times a sine is just sine squared. So across the top, the multiplication becomes sine squared. On the bottom, it becomes cosine squared. Well, it's better. I'm only dealing with 2 functions, but it is a fraction. It's not the best. I look back at the toolkit, and I remember, oh yeah, sine over cosine is tangent. So sine squared over cosine squared is tangent times itself, which would be tangent squared of x. Okay. And so there's the answer to question number 18. Number 19, though, it has the Pythagorean nature. It starts tangent squared, cosine squared, plus cosine squared. The thing to realize about this is that it's Pythagorean, yes, but not all of it looks as Pythagorean. For instance, Pythagorean problems do not have multiplication in them. So if there's multiplication, that has to be managed before we can really look for the Pythagorean identities. And so when I look right here, I see this multiplication that happens right there, and I say, that's not okay. I've got to treat that part of the problem like I treated 18. So I'm going to make the tangent squared be a sine squared over a cosine squared, and that's times cosine squared over 1. I still have my plus cosine squared, but that's not something I need to worry about right now. It's this multiplication problem that I want to clean up. And this would cancel. A cosine squared over a cosine squared cancels. I'm left with sine squared plus cosine squared, and that equals 1 by Pythagorean definition. Okay, we've only got just 4 more left. We're almost there. Let's see, we'll add a page here. Okay, on question number 20 and 21, I'm going to start the solving process, and then I'll go to the unit circle. So 20 says 2 cosine of x minus root 2 equals 0. And so first thing I do is I'm going to add root 2, right? So I'm trying to solve for x, or more specifically, at least isolate the trig function. So 2 cosine equals root 2. And now if I divide by the 2, I'm looking for a place where cosine equals root 2 over 2. I'll go to that in just a second. We're not done, but just bear with me. Then over here on number 21, we have 7 tan minus 7 equals 0. So the first thing we would do is we'd add the 7. And then we're going to say that 7 tan equals 7. And we divide by 7. And tan of x equals 1. Okay? So I've got the cosine of x equals root 2 over 2. And I've got the tan of x equals 1. So I'm going to go to my unit circle at this point. The cosine, remember, is the x value. And I'm looking for x values of root 2 over 2. I see one right there at pi over 4. But I also can find one right here at 7 pi over 4. So when I go to write the answer for the first one, for 20, I'll say that x could equal pi over 4 or 7 pi over 4. But I remember that these are waves. They're not just somewhere on the circle. It's actually very repetitive. And so I need to add to them a way to say, including all the ones you get if you kept going around the circle forever. And that would be a full circle is 2 pi. N means as many times as you want. I'm going to add 2 pi n to both of those answers. Okay. Over here on number 21, okay, we still have tangent is equal to 1. Now, if you didn't write down all of the tangents along the outside of your circle, this is going to be a little bit harder. The tan of pi over 6 is root 3 over 3. The tangent of 45 is 1. And the tangent of 60 degrees, or pi thirds, is root 3. Now, these repeat as they go around the circle. The signs change, but generally speaking, they do work for you. They help you a lot. Now, we were looking for a place where the tangent is 1. Well, it just so happens to be here at pi over 4 again. The thing is, though, when you say that you can use pi over 4, you can add to it a tangent's period. But remember, a period of a tangent is not the same as a sine or cosine. Instead of being 2 pi n, it's just pi n. Now, when I go to the unit circle, I want to look and see if there's another answer. Well, down here, a negative and a negative that match, stacked on top of each other, this is going to give me a tangent of positive 1. So I could technically write 5 pi over 4, but the thing with 5 pi over 4 is it includes, or it's a little repetitive. So I don't have to have it in my, sorry about that. So it also happens at 1. That is exactly pi, or 180 degrees, away from the original answer. So when there's a tangent, we do get to avoid writing the second one, but it's not wrong to include extra information. It's just redundant, and it shows that you don't really feel confident or have a lot of knowledge about what you're doing. You're kind of just, I want to say fudging it, but you kind of are. Okay? Well, let's go ahead and look at the last two here. We're going to look at the sum and difference stuff. Now, if you don't have the sum and difference formulas written down, some of this is going to seem a little confusing. Did you catch that little pun there? Some of this is going to seem kind of funny or a little confusing. Well, here we go. All right. The first one we're going to do is number 22 is the cosine of 195. Now, 195 degrees is not on my circle, but if I take 150 degrees and I take 45 degrees, I can add those to get 195. So that's what I'm going to do. I'm going to replace this with the cosine of 45 plus 150. And the order here doesn't really matter. It should work itself out either way. Well, the cosine formula says that we take the cosine of the first thing times the cosine of the second thing, 150. Now, this is important. The sine is always the opposite here of what we had up there. So we're doing a minus of the sine of 45 and then cosine, or sorry, sine, gotta stay with my sine here, of 150. Now, the rest of this is about reading the circle. If I go back up to the circle and try to think, what is the cosine, or x value, at 45, I realize it's root 2 over 2. Okay? And then the cosine at 150, that's over here on the left, and the cosine is negative root 3 over 2. So that's times a negative root 3 over 2 minus the sine of 45, if I went back up there, is root 2 over 2, and the sine of 150 is 1/2. If I multiply on the left, I get negative root 6 over 4, and I get minus root 2 over 4. When I combine those, I get negative root 6 minus root 2 all over 4. And there's the answer. Whoops, I lost my negative there. Let's bring that back inside. There we go. So that is negative root 6 minus root 2 all over 4. If I continue the process for the next one, 23, it's the sine of 75 degrees, which I know for my circle can be the sine of 30 plus 45. So the sine formula says that we take the sine of the first thing times the cosine of the second thing. The sign will match here, so plus the cosine of the first thing times the sine of the second thing. I'm going to use my little trig knowledge so I don't have to go back up to the circle. If you look at the 30-degree angle for the circle, the sine, or y value, is 1/2. The cosine of 45, the x value is root 2 over 2, plus the cosine of 30 is root 3 over 2, times the sine of 45 is root 2 over 2, leaving me with root 2 over 4 plus root 6 over 4, or root 2 plus root 6 all divided by 4. That's the whole test. Hopefully between the two videos it's enough to make sure you have everything you need. Good luck, and we'll see you in class.